And so within those topics, let's look at our practice exam here. So in the figure to the right, which term best describes member A, B, C? So this is asking about zero force members, two force members, multi-force members. And so A, B, C, since there's three locations, this is a multi-force right there. And then B to D, that's a two force member because there's only two locations right there. That's our first step. If we were asked to solve this problem, is to find the types of members that we have, so that then when we are asked to solve this problem for the figure, find the magnitude of the reactions at point C. Well, we have some choices for FBDs. We know that B to D is a two force member, so that means that we know the line of action goes between B and D. We can do an FBD of the whole thing. If we did the whole thing, we would do a CX and a CY, which is what it's asking us for. Even though this is a pin, because this is a two force member, I'm going to draw this as an FBD right there. And then we have our 400 newtons going straight down. So that one, there's three unknowns. We can solve for those three unknowns with our three equations of equilibrium. The other FBD that would have worked would have been the FBD of just CB to A. So that one right there, we would have a CX and a CY right there. And then at point B, I would do an FB to D. And I'm not sure if FB to D goes up or if it goes down. I'm just kind of guessing there that it's going to go up. My math will tell me if it goes opposite direction. We have 400 newtons right there. So remember, our FBDs, what we've talked about is pick an FBD with knowns and not too many unknowns. The only way to figure that out is to either visualize the FBD or to draw the FBD. Would we ever do an FBD of this two force member? Probably not, because the only thing that would have is just, a force in B to D going this way and a force in B to D going that way. There's no known values on there, and we really can't solve for anything by doing an FBD of just a two force member. So that's our hardest part of these problems, is picking those FBDs. But if you think about the complete enumeration of finding an FBD with knowns and not too many unknowns, that should hone you in on that correct FBD pretty quickly. And then you can, once you have that FBD, solving it is really should be the easy part. That's the summing forces and summing moments. They ask us which statement is true about member B to D. We have, in this next problem, we've talked about how this is a two force member in B to D. So the internal normal force is 0. Well, if we have a two force member, and we've talked about this, if we have a straight two force member, we have an N, a V, and an M here. And then we would have like our force from B to D down here. Well, is N going to be 0? No, that's not true. The internal normal force is constant along the length of the member. Does it matter if the cut is here or if the cut is here? Actually, it doesn't. It's not going to change. So that is a possibility. The shear force and bending moment vary. Well, what is the moment and the shear? It's equal to 0. When we have a straight two force member, it's equal to 0. So that one is not true. The shear force remains constant, but the bending moment, that's not true. There are no internal forces. Well, there are internal forces. It's just the only one is the normal force, just like a truss member. When we did trusses, we only had the normal force in there. Any questions about that one? Okay. Moving right along here, we have another machine or frame here. Considering that the force from the punch D on surface E is required to be 500 newtons, so they're telling us right in here is 500 newtons right there. The vertical surfaces on the punch are frictionless, so we have some frictionless vertical surfaces here. Draw a free body diagram in the box below to solve for the internal normal force on length B to D. Well, our FBD if they're telling us to find the internal normal force in that short link, well, we have to cut through it, don't we? So we definitely have to cut through it. And going back and thinking about, okay, our FBDs need to include knowns. And so that means, well, we better include the 500 newtons down here. So that keys us in pretty quickly into that FBD right here. And so we'll draw that FBD in a second. Let me check this question in the chat. Can we have a two-force member with a fixed support on one end? Or that would not, if it's got a fixed support on one end, it is not a two-force member because it has a moment. So two-force members, they only have two locations of forces and no moment. As soon as there's a moment, whether it's a reaction or an applied moment, it is no longer a two-force member. And actually that reminds me, we should have talked about the type of members we have in this. B to D is a two-force member, isn't it? A, B to C, this is a multi. So that is really going to help us as well, because if we're looking for the to find the internal normal force on link B to D, well, there should only be a normal force because it's a two-force member. So let's draw our FBD here. We cut through that right there, and then we're leaving this pin attached because we want to incorporate this 500 newtons along the base here. If this is a normal force, it's got to be acting and pushing force, and so we're going to have the normal force at point E right there. And actually that's what the one they're telling us is equal to 500 newtons. And then this is a two-force member, so we know the line of action is here, and so we can think about this as being, I can draw it up and to the left, I can draw it down and to the right, but basically we have the normal force in B to D, and then our B, our shear force, and our M would be equal to 0. Now, if I look at this FBD here, I can't, I'm missing something because there's only one thing acting in the x direction. I have NBD is acting in the x direction. And so we're also going to have a normal force along these frictionless surfaces, these vertical surfaces here. And we need that just to meet equilibrium. So based on my NBD going up this way, I might draw my normal force here. We can call that the normal at D right there. Now I can meet equilibrium in the x direction, right? So now when I sum forces and the x is equal to 0, we're going to have an ND and then minus the NBD times the, let's see, that was given at a 20-degree angle right there, times the sine of 20 is equal to 0. So I have a sum of forces in the x, we can do sum of forces in the y, and then we can solve for the normal force in B to D. So we have two equations with two unknowns for this problem. The tricky part on this one is that normal force over here at point D. And it's because these vertical surfaces are frictionless, right? But we do have to be touching one of those vertical surfaces there. It's not going to be touching both at the same time unless there was like a clamping force on there. But if they're frictionless, it's allowed to move up and down. It's going to be touching one of those surfaces. And so it doesn't matter which one it touches. We can assume it's on either one. Our math will tell us which one is actually touching. Any questions about that? The next one, we're asked to find the internal force. We already talked about doing that to actually find the value there. We have the FBD. Go into our sum of forces in the x and sum of forces in the y. That will allow us to solve and find that actual number. Moving on to number 6 here. Same machine, but a different loading scenario. They're asking us to find the force P. So we want to find this over here now. That will result in an internal normal force of 320 newtons in the link. Okay, so again, they're giving us this normal force here in that link of 320. So that's the normal force in B to D right there. Well, that's our known value. So we better include that in our FBD. And then what if what if we did, let's just look at our options. Well, we could go back down here. Well, that doesn't include what we're trying to find. That doesn't include P. So then what if we did an FBD of this right there? Let's take a look. How many unknowns is that going to have? Let's see, we're going to have right there, we're going to have our P. That's what we're trying to find. We have our short length that we cut through right here. We cut through that one. And we know that there's a normal force right here of 320 newtons right there. And then what about at point A? Well, A is a pinned support connected to a multi-force member. So that would be an AX and an AY. So in this FBD, then we have 3 unknowns and we have 1 known there. So we can sum moments. Actually, it looks like if we sum moments about A equals 0, we will get an equation that will allow us to find P. So again, following that same process for picking our FBD, what are our options? And then identifying the option that doesn't have too many unknowns and has known values. Okay, moving on to internal forces now. Which scenario represents positive internal loading for a section for the left side of a beam? Circle the correct answer. We actually did a quiz on this one. Remember, it does not matter what the forces are that are applied to this. If we are going to the left side of a cut, our V is going to always go down, M is always going to go counterclockwise, and N is always going to go like that. So which one is it? It looks like it is, where is it? It's this one right here, right? So down, counterclockwise, and to the right. If we have a cut and we're looking to the right, it doesn't matter what the loads are, it'll always be like this. M is going to go clockwise, V is going to go up, and N is going to go to the left. So it'll always, always, always be, that's our positive sign convention. It doesn't matter what the loading is applied to it. If you're going to the left or the right, it's one of those two scenarios will always be those directions for V, N, and M. Okay. Now, how about actually implementing this and finding the magnitude of the internal bending moment at point J? The diameter of the pulleys is given and the angle alpha is 30 degrees. So if we want to find the bending moment at J, well, we better cut through point J right there to expose that bending moment. So we draw our FBD here. There's our cut. And actually, which side of the cut should we go to? Should we go to the right? If we go to the right of the cut, we got to go all the way and then all the way over here, right? We got to go all the way to the right. Well, we don't know what's going on right here at point C. We don't, well, we know it's a fixed support, but we don't know what CX, we don't know CY, and we don't know M. We could find it, but why do that when we could just go to the right or to the left and we have our 500 newtons right here. So let's go to the left of that cut there and we have our pulley that's right here. And then we're going to have our forces that are acting on that. We'll have a 500 newtons going here. We'll have a 500 newtons here. We know where all those distances are, what all those distances are, and then we would draw our V, our M, and our N. We get some moments about the cut equal to 0, and we can find that M at point J. By summing moments at the cut, we solve for MJ. Okay. Moving right along here. Any questions about that one? Okay, number 9. This one we're asked to find the shear force at point K. So again, let's cut through point K there. And let's go to the left again, because then just like before, we don't have to worry about finding CX, CY, and MC right there. Now, notice that when we close the loop, we are cutting through that string right there, right? Anytime, anything you cut through, you should include that in your FBD. Anytime you cut through a physical thing, you have to, right, you have to replace that physical object with a force and or moments. We can have we have our pulleys here. So we've got a pulley there. We've got a pulley here. And then, so let's see, we're going to have 500 newtons going straight down there. Now, we didn't cut through this segment of rope up here, but we did cut through that segment right there. So there's another 500 newtons there. And then at K, we're going to have our V, we'll have M. And in this one, we defined our positive sign convention on internal forces. Really, a lot of it's based on the top and the bottom of the member there. Notice that it's not asking you for the sign on this one, so you don't have to worry. If it's a vertical member, we know that really you have to define the sign yourself. Define what's the top and what's the bottom. For us, if we're going to do anything with a vertical, we're just going to ask for the magnitude. So here's our FBD. It's got a 500 Newton, another 500 Newtons. We can sum forces in the X direction equal to 0, and we can find or solve for V there. We have the angle of alpha right here is equal to 30 degrees. And so when we sum forces of the X, we can figure out how much of that 500 Newton, right? It'd be 500 times the sine of 30. And then that's actually the only other thing besides V in the sum of the forces in the X direction. Okay, number 10. We are asked, what are the reactions at A and B for the beam shown with a distributed load of 2,000 pounds per foot and 600-pound concentrated force? So this is just finding these reactions here, right? AY, we've got a BY right here. Got all of our applied forces. We'll have an AX as well. And so this is just summing moments about A is equal to 0 and finding BY, and then we can sum forces in the Y and we can find AY. This is just finding support reactions of a beam, which should be really like 99% of us, 100% of us should be getting this type of question correct. And this is needed if we were asked to find the internal forces somewhere, right? We have to find the support reactions if it's asking about those internal forces. Like if they asked us to find the internal forces between A and B, well, we need to know what's going on here or here in order for us to do that next FBD there. So this is a step in the process there. Okay, number 11 is asking the correct relationship between the distributed load, the shear force, and the moment. And so when we have been doing our V and M diagrams, we've been talking about how the slope of V is equal to W and the slope of M is equal to V. Those are really our two main equations that we have for are mathematical relationships between W, V, and M. So the slope of V, well, slope of V is dV dx, right? Well, there's a dV dx is equal to W. And then the slope of M, so it's this first one right here that we are looking for. Okay, number 12 here. For the beam, what is the absolute value of the slope of the shear diagram between points B and C? So an application of our previous one, the slope of V is equal to W. So between B and C, our W is equal to 2,000 pounds per foot. So that is the slope of the shear diagram. Number 13 here. Note the distributed load is now equal to 1,500 pounds per foot, and the resulting reactions are given, AY, BY, both acting upward. This did not transfer over. That should be 1,500 pounds per foot on that picture right there. Both are acting upward. At what point on the beam, as measured from A, is the shear equal to 0? Well, what does our general shear equation look like for this beam? Let's draw it directly above right here. So if we know this AY is equal to 2250. We know BY is equal to 750. Our shear diagram is going to start out at, our shear diagram is going to start out at 2250, and it's going to be a straight line because our slope is equal to 0 because the distributed load is equal to 0. And then this 750 is going to pop up that shear by 750. Then in this region, we're going to be there at 1,500. Our slope will be at 1,500. So our shear diagram is going to slope down like this till we get to this spot right here where we have a 600-pound load right there at the end. And that is going to give us a V equal to minus 6,000 right here. And we could figure that out by drawing a little FBD real close to point C right there. Well, what do we have? We have this 6,000 pounds is going up, and we have V. Which way should we draw V for positive? We're going to draw V going up as positive when we're looking to the right of a cut. Our distributed loading, as we get really, really close to C, so as this approaches 0, as that distance there approaches 0, our W approaches 0, or the contribution of W approaches 0. So you can see when we sum force in the Y, we're going to find that V is equal to minus 6,000 pounds for that one. So we did the general shear diagram because we need to know what segment is that going to be in. Well, what segment are we going to get 0 shear? Well, it's going to be in this segment between B and C. It's going to be in this segment with W equal to 1,500 because that's where we have a slope. In the other segment, we're going to be flat. So it can't be in that piece right there. So then we need to figure out our equation for the shear diagram. We need to come up, what is V of X? Because if we know V of X, then we can set it equal to 0. Well, we can make a cut in that region now. And so if we did a cut here, we have our distributed load that's acting down 1,500 pounds per foot. We have 6,000 going up, and then we would end up with right here our V as a function of x is going to be going up. That's the only one I'm going to draw. Remember that x of 0 is way over here, and that this distance is equal to x. So that means that this distance right here is equal to 10 minus x, because 10 is the whole distance from 4 feet plus that 6 feet right there. So we have 10 minus x. Now we can sum forces, and the y is equal to 0. We've got a v of x minus 1,500 times 10 minus x plus the 6,000 is equal to 0. We can set this to 0. So set our equation to 0. So we'll take our 1,500, let's see, times 10 minus x minus 6,000, set it equal to 0, and we will find what value of x we need where the shear is equal to 0. Yes, the similar, so Colin was asking that if I could explain the similar triangle approach for this one as well. Yeah, the similar triangle one uses basically the fact that we know this whole triangle right there. If we know the value of the shear is 2250, and then it gets up to right here, our value is 3000. So if we know the height of this triangle, we can then find this other triangle in here. So basically we take our purple triangle, which is that's 3,000 to really our height is equal to a 9,000 right there, because this is 3,000, but this is minus 6,000 right here. So that gives us a total height of 9,000 and is to 6 feet. And then the orange triangle, we know this is a height of 3,000, and we would be looking for that distance there. But that only gives us from here to here. The answers at what point measured from A, so we would still have to add in that 4 feet that's left. Does that make sense? I think doing it with the equation, making a cut and doing the equation is kind of a fail-safe method of doing that rather than trying to manipulate some sort of similar triangle there. We can always do the cut approach. Okay, let's go on to the next one here. This is the one where they're asking us to just do it all from scratch, to draw the V diagram and to draw the moment diagram on here as well. They give us AY and they also give us CY. So AY is given over here as 4.8 kilonewtons. And then CY is also given to us. What is CY? Oh, do I not have it? I guess I don't have it on these slides. 7.2, thank you. 7.2 for CY. Now, we can do this a couple of different ways. We can make a cut. We'd have to do 2 cuts. We would do 1 cut between an A and B, and we'd come up with our FBDs. We would figure out V as a function of X and M as a function of X. We'd have another cut here. So we could do cut 1 and we could do a cut 2. We can certainly do that way, or we can do the graphical approach for the V and the M diagram. So I'm going to go ahead and let's do the graphical approach. I'll set up the horizontal axis there. In this graphical approach, we follow the loads around. So 4.8 is going up. Well, that tells us that our shear is going to start up here at positive 4.8. So 4.8 goes up, that jumps us up to 4.8. That's where we start, is at 4.8. Now we jump in and we are in this distributed load all the way till we get to point B. Well, that's the slope of our shear diagram. So we know that our slope is going to be equal to -2 kilonewtons per meter. Now, if we're going 3.2 meters, doesn't that mean that we're going to change, or delta V is going to be -2 times 3.2, because for every meter, we're going to drop by 2 kilonewtons per meter, and we're going 3.2 meters. So 2 times 3.2, my calculator wasn't even on, I can do that in my head, 6.4. This is also the area under the shear diagram over that whole region. The area is equal to 2 times 3.2, which is our delta V. So we know we're going to go -6.4, but that's our change. We're starting at 4.8. By the time we get to here, we should be at 4.8 minus 6.4. And so that's going to be, let's see, -1.6. So our going to look something like that. And right here, we know this is going to be 4.8 minus 6.4 is going to be equal to a 1.6, negative 1.6. That's our value of V right there. We hit this 4 kilonewtons going straight down. That's going to jump us down by 4 kilonewtons. So this point right here is going to be -1.6 minus another 4, minus 5.6. And then for the last section between B and C, we are still in that distributed load. And so our slope should still be the same as it was in that first part. Our slope is still -2 kilonewtons. And then we can also figure out the area under this last part. The area from B to C is going to be 0.8 times 2. So a -1.6. So that V right there is going to be -5.6 minus another 1.6. And look at that. It gets us to -7.2. That's a check. We should end at the value of that support reaction right there. Now, regarding where V is equal to 0, we are going to need to figure that out, because we are going to draw the moment diagram next. And so where V is equal to 0 right here, that's where M is maximum. And we're going to need to find that to do our moment diagram. So this one, maybe, why don't we take a look at the similar triangles on this one? Wouldn't we have this big similar triangle here? Let's make this 3.2. So that would be like, I'm drawing basically this triangle right here. So that's 3.2. What would the height of that be? The height would be 6.4, right? That's our total distance from 4.8 to -1.6. And then we want to find this similar triangle in here. Now we know that the height of this one is 4.8, and that one is our x distance that we're trying to find. So we could go x over 4.8 is equal to 3.2 over 6.4. We could find that value for x. Or yes, it would also be, great question. We did similar triangles, but can we figure out, just by looking at our picture here, can we figure out that V of x is equal to the y-intercept 4.8 minus the slope times x? And so we could just take this 4.8 minus 2x, set it equal to 0. and we would find that x is equal to 2.4 feet. So either one of those will give us that answer of x equal to 2.4. Okay, let me draw the shear diagram on here, and then we already drew it, so I'm basically just copying it back on, and then we will do the M diagram. So here's our V, and then let's do the M right below that one, right there. So our V diagram looked like this here. So we started there, we went down like that, we dropped, and we went down here. We know that this is 2.4 meters. This was 4.8 minus 1.6 and a minus 7.2. Oh, sorry, this is minus 5.6 minus 1.6 was that spot up there. So now our M diagram. M at a roller or a pin at the end of a beam, M is going to start out at 0. So we know M is going to be equal to 0. And then we can do M entirely based off of our shear diagram, because the slope of M is equal to the value of V. And so our value of V starts out as a big positive number. And it gets smaller and smaller until we get to 0, which is right there. And so our M diagram, let me do a different color. Our M diagram is going to go up like this. The slope is going to start decreasing until we get right there. Our slope is going to be equal to 0 at that spot. And then what happens? Our slope starts to become negative right there. And then right here, where we go from on our shear from minus 1.6 to minus 5.6, that does not cause a jump in our moment diagram. What it does is it just causes a change in the slope. So our slope right here is equal to a minus 1.6, but then our slope right here is equal to a minus 5.6. So that's all that does, and we should end up back at M equals 0 because it's a pin at the end of the beam. That pin does not resist rotation whatsoever. Now, we will need to find not only the shape, but we need to find what is the moment right there. What is the moment at that spot? What is the moment at that spot right there? So we need to find those two things. Well, we can do that by finding these areas. If we can find this area, which is just 1/2 of 4.8 times 2.4, that'll give us the change in M from here to here. So we can find that, and that'll give us that M. And then what about this little tiny triangle right in here? That little triangle, we can call that A2. That'll be 1/2 of whatever is left out of the 2.4, 3.2 minus 2.4 times the height of that, which is 1.6. So then the area 2, and that one's going to be a negative. This will be a negative area. And so it's going to drop us down from this maximum down just a little bit to that next point. And then the area, this last one of this trapezoid right here, that area right there, area 3, would be how much change we're going to get from that spot down to here, which should get us back down to 0. So this is all using those mathematical relationships, the graphical approach. Like I said before, you could do this with 2 cuts, come up with your equations, and plot those equations. Remember, for looking at V and M diagrams, I would recommend that document that's part of hands-on number 6. That's got a lot of key cases. in there. I think having that handy, taking advantage of the open book, open notes, having that handy during the exam. There's that, there's the PDF that has all those cases on there. Or if you want some last minute review, that hands-on number 6, you can do it unlimited times. Don't be afraid to go in there and give it a try before the exam, and then maybe, finish it and get the right answers after the exam. Or, I think it's that hands-on number 6 would be good studying for V&M on the exam. Okay, let's wrap up here with a few problems on cables. And these ones, I'm going to focus on the FBDs and picking that FBD. If DB is equal to 3 meters, determine the tension in cable AB. So, well, if they're asking us to find the tension in cable AB, well, we better cut through it. And then we better go to the right, because to the left, there's really not a whole lot of information there. So if we do an FBD to the right there, we know the slope of A to B has a known slope because they give us that 3 meters, and we know the horizontal distance is 4 meters. We have a known slope right there. We have known applied forces. We would also have an EX and an EY over here. And we can sum moments about E equal to 0, and we can find that AB right there. So we picked that FBD based off of what their problem is asking us for, and that it's a known slope right there. Number 18. In this one, they say if YB is 9 and YD is 8, the maximum tension will be found in which cable? Maximum tension is always going to be in one of the end segments. It can never be in the interior segment, because the steeper segments are always going to be on the ends. They can never be in the middle. And so we just need to figure out which one of these is steeper. Well, YB is 9 feet. So that means this is a 9 and 12. And then YD over here, this is a 12. YD is 8, but the whole height of that is not just 8, it's 12. And so this is a 12 slope. This is a 9 12 slope. So this one is steeper in that case. And watch out on these cable problems. Just the nature of these problems is that sometimes things are measured, to the lower support and not to the top support. So watch your dimensions on there to make sure that you're getting, you didn't call this one an 8-12, because that is not the correct slope. It's a 12-12. Even though YD is 8, we got to add that extra 4 feet to get from A up to E. So watch your geometry, right? That's just kind of, watching your geometry on the tests when you're going fast, but obviously, yeah, you're going fast, right? But don't be afraid to slow down for a second and just be like, okay, yeah, is my geometry all good? Or, in other parts of these problems as well. Okay, in this one, DC is 7 feet. Find the tension in cable D to E. DC is equal to 7 feet. And they give us, we have all these known loads. We did an example problem like this in class, at least we started it. You had them like this on the homework, where there is no known slopes. These are all unknown slopes of this based on where they gave us. They gave us the 7 feet and they gave us that 6 feet. That means because there's an extra point in between all the known dimensions, I don't know what the slope of A to B is. I don't know A to C, C to D, or D to E. So this is what we have to utilize, is we have to utilize the 2 vertical distances that they do give us, the 6 feet and the 7 feet in this case. And that's going to be with an FBD of the whole thing. So if we did an AX and an AY and an EX and an EY, this has 4 unknowns. So we're not going to be able to solve for anything, but we have at least one, like If we sum the moments about A is equal to 0, we'll come up with an equation with EX and EY. So we're going to get an equation that has EX and EY in it because we know that 6-foot distance to EX, right? The line of action of EX is 6 feet above point A. Now our next FBD that we need to do is an FBD that's going to utilize the 7 feet and include EX and EY. So we're going to do this FBD of CDE. So C to D to E right here. And we'll get an EX and an EY again. The key is that we know this distance right there is 7 feet, even though we don't know the tension in C to B, even though we don't know the angle of C to B. By summing moments at point C, we'll get another equation with CX, or not CX, with EX and EY. Now we have 2 equations with 2 unknowns, and we can solve for those 2 unknowns with those 2 equations. And then to find the tension in D to E, we will square root our EX squared plus EY squared. So using the Pythagorean theorem to find the tension in that end segment based on knowing our EX and EY. And then I see a question here from a problem ago. If they had the same slope, they would have the same tension. That is correct. If they had the same slope, they would have the same tension. Now, this one's going a little bit different direction here. If EX and EY are known, so now instead of asking us to solve for EX and EY, if we know EX and EY, they want us to solve for D to C. Well, it's the same FBD we just talked about, and we would still sum moments about C equal to 0, because then DC would show up in we could use that to solve for DC, that same FBD. So we're incorporating DC into our FBD, we're incorporating EX and EY, and then I believe the last problem here just asks us to find that value for DC, and that would be by summing moments about point C, you can find that distance to C. Okay, and that wraps up the practice, all the problems on the practice exam at that high level. Good luck.